We compute determinants using a formula for matrices of small size 2 by 2 and 3 by 3, or by using elementary row operations for matrices of larger sizes. Today, we are going to discuss other methods for computing the determinant that are particularly useful in special situations. We consider the following theorem, which describes the determinant of a matrix with a block of zeros. Let P be a matrix with a block of zeros. So this means that P has the following structure. We represent n as a sum of k plus m and select in P the following submatrices. So we have a k by k submatrix in the top left corner, m by m submatrix in the bottom right corner. Then whatever is in this corner, is in this m by k corner, we call it B, and require in the upper right corner of size k by m, we have all entries to be 0. In this case, we make a claim that determinant of this matrix P is equal to the product of determinant of a matrix A times determinant of a matrix C. Let us give a proof of this theorem. So we write down the formula for the determinant of the matrix P. So this is the sum over sigma in Sn minus 1 to the power sigma. So we have the product P1 sigma of 1 dot 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 Pk sigma of k, Pk plus 1 sigma of k plus 1 dot 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 Pn sigma of n. Now we analyze this sum. So if for some I from 1 to k we have sigma of I is greater than k, then the corresponding term in this sum is equal to 0, since in this case Pi sigma of I is equal to 0 because this entry will be in this block filled by zeros. Thus, we only need to consider those sigma, such that for I between 1 and k, sigma of I is also between 1 and k. So then we conclude that sigma permutes elements of the set from 1 to k. And so in fact, it will assume all values from 1 to k on this set. Since sigma is injective, so this means that these values cannot be assumed on indices that are greater than k. So then we also have that sigma applied to the set k plus 1 to n will produce values from the same set k plus 1 to n. So pictorially, we can have like two groups of indices. So we have the first k indices and the last m indices. And sigma will permute indices in the first group, n will permute indices in the second group. So we can think that sigma is not a single permutation, but a pair of permutations. So we have a permutation tau of the first k indices and the permutation mu of the last m indices. And now we can think of sigma as a pair of these permutations. And it's easy to see that the parity of sigma is then equal to the product of parities of these two smaller permutations. And now, if we come back to this formula for the determinant, we can see that we can write it as a sum over tau in sk and mu in sm. So then instead of parity of sigma, we'll write it as parity of tau times parity of mu. Now, here, sigma of 1 through sigma of k, all these indices will be less or equal to k. So this means that these entries are taken from this block. And so this can be written in terms of matrix A. So here we will have A1 tau of 1 dot 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 AK tau of k. And when index is greater than k, then the value of sigma are also greater than k. So this means that all these entries will be taken from block C. Here we will have C1 mu of 1 dot 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 Cm mu of m. And we can see now that these factors as determinant of a matrix A times the determinant of the block C. And this proves our theorem. Since determinant of a matrix does not change when we take the transpose, so this result also applies to the matrix of block type, where we have the block of zeros in the bottom left corner. So to prove this formula, we will just take the transpose of this matrix and we'll come to this case. As a warning, let us mention that this shortcut does not apply to matrices without a block of zeros. So if we cut down, say, a 4x4 matrix into 4 2x2 blocks, then this determinant will not be equal to this formula with the blocks of this matrix. So, of course, in general. Another special situation where computation of determinant is easy is given by the following theorem, that determinant of an upper triangular matrix is equal to the product of diagonal entries. A matrix is called upper triangular if all of its entries below the main diagonal are equal to 0. This theorem says that the determinant of such a matrix is equal to the product d1 times d2 times dn. To prove this theorem, we consider the following block decomposition. So what we'll do is we'll take a 1x1 block in the top left corner. So then, because the matrix is upper triangular, all entries below d1 are equal to 0. And there are some entries in the top right corner. And then what we see is that this becomes a matrix with a block of zeros. So just of this form with k is equal to 1. And so we can conclude that determinant of the upper triangular matrix is equal to this 1x1 determinant, which is d1, times determinant of the smaller upper triangular matrix. So we have d2, dn, then all zeros here and something here. Right? So this is the second block here. And proceeding, iterating this idea, so we will eventually get that this determinant is equal to the product d1 times d2 times dn. And this proves this theorem. As a corollary, we get the same result for the lower triangular matrix. So if we have a lower triangular matrix, so this means that we have d1 through dn on the diagonal, we have zeros above the diagonal and something below the diagonal. Then this determinant is also equal to d1 times d2 times dn. So we obtain this corollary by taking the transpose of this matrix, and we know that determinant does not change under the transpose. This provides a shortcut for our main method of computing the determinants of large matrices by using elementary row operations. So if at some point we reached an upper triangular matrix, then we don't need to do any further computations or any further row reduction. Here we can just conclude that determinant of an upper triangular matrix is the product of diagonal entries and just stop there. Another easy corollary of this is that determinant of a diagonal matrix. Right? So if we have a matrix where all non-zero entries are on the diagonal and we have zeros below and zeros above. So this is still equal to the product of diagonal entries. So this is because this matrix is simultaneously an upper triangular and a lower triangular. But since diagonal matrices will play an important role later in this course, so it's worth pointing out this observation. Next, we are going to discuss cofactor expansion of the determinant. But before we do this, we need to introduce some pieces of terminology. So, definition. A minor of a matrix A is a square submatrix in A, obtained by removing some rows and some columns in A. And the second definition, a cofactor Aij of a square matrix A is the determinant of a minor of A obtained by removing row I and column J in A, multiplied by -1 to the power I plus j. So let's do an example. So suppose A is the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. And we want to calculate the cofactor A21. So this cofactor corresponds to this position here. What we do is we cross out column that corresponds to this position and the row that corresponds to this position. And what we get is we get the determinant of a resulting 2 by 2 matrix, 2, 3, 8, 9. And we multiply this by the sign, which is -1 to the 2 plus 1. So now this becomes -1 times 2 times 9 minus 3 times 8. So here we have 18 minus 24. So this is -6. So times -1. So this is +6. This is the value of cofactor A21 for this matrix A. And we point out that these signs, -1 to the I plus j, form the checkerboard pattern. So they go plus, minus, plus, minus, plus, minus, plus, and so on. Now we can state our theorem, which is called cofactor expansion of the determinant along a row. This theorem says that determinant of any matrix A is equal to the sum over j from 1 to n of aij times aij. And this formula holds for every I from 1 to n. So in this formula, I is fixed and could be arbitrary index from 1 to n, and j runs in this sum. So what we are doing in this formula is we fix one of the rows in a matrix and then have a sum of products of entries of this matrix in this row times the corresponding cofactors. And this formula explains the name why this expression is called the cofactor. Let us state a corollary that we obtain by applying this formula to the transpose of matrix A. So we get corollary, which is column expansion of the determinant. So for every j from 1 to n, determinant of A is equal to the sum over I running from 1 to n, aij times aij. So here, this expansion is taken over column number j. So we fix one of the columns in the matrix, and we take the cofactor expansion of the determinant along that column. From now on, we will use the following shorthand notation. So instead of writing the word determinant of a matrix A, we will write matrix A in the vertical bars, and this will stand for determinant of the matrix. Computationally, the method of cofactor expansion works very well on matrices with lots of zeros. So let's compute the determinant of the following 4x4 matrix. So here we see that the third column in this matrix has many zeros. If we take cofactor expansion of the determinant along the third column, then most of the terms will vanish because aij will be equal to 0. And so what we get is that we have here a single non-zero entry. So we will get that this determinant is equal to, so this entry is A32 times the cofactor A32. To write down this cofactor, all we have to do is we have to cross out the column of this cofactor and also the row of this cofactor. And then we will get a 3x3 matrix. So this determinant is equal to, well, the entry A32 is equal to 3 times we have the sign. So using this checkerboard pattern, or simply from the fact that 3 plus 2 is an odd number, so we see that the sign here is going to be negative, and we get the following 3x3 determinant. So 3, 1, 2, 2, 0, 1, and 5, 4, 3. Now here we could have used the formula, but as a practice and taking advantage of the fact that we still have a 0 in this matrix, let us compute the cofactor along second row. So what we get here is, well, this factor is -3, times, now we evaluate this 3 by 3 determinant. So we have the entry of 2 here, and now we need to take the cofactor. So using our checkerboard pattern, so here we have a plus, so here we have a minus. So this means that the sign here is going to be -1, and then we delete the second row and the first column, and we get a 2 by 2 determinant, which will be 1, 2, and 4, 3. And so the next entry is going to be 0, and one more entry will have this 1. So we have +1. The sign again is -1 here. And if we remove second row and the last column, then the 2 by 2 determinant will be 3, 1, 5, 4. So what we get is we get -3 times. So here we have -2 multiplied by, so using the formula, we get 3 minus 8, and plus -1 times 12 minus 5. So what is this? So here we have -3 times, so this is -5 times -2, this is +10. And so here we have 12 minus 5, that's 7, and it comes with a negative sign. So we have 3 times -3, so the answer is -9. So the conclusion is that the determinant of this 4 by 4 matrix is equal to -9. Let us prove this cofactor expansion formula. So we consider row number I in matrix A. So here we will have this AI1, AI2, ... AIN. And then we expand this row as a sum. We write AI1 0, 0, 0 plus 0 AI2 0, 0, 0 plus ... all zeros, and the last entry AIN. So the sum of these rows is equal to the original row number I. And then, using the properties of the determinant, we can write the determinant of a matrix A. We can expand it according to this summation in row number I. So we can write the sum j goes from 1 to n. And so here we take the determinant. We are in row I, so we have zeros, and then Aij in column j, and 0 elsewhere, and the rest of the matrix is unchanged. Next, I want to move row number I to the top row. So what we are going to do, we are going to switch row number I with rows above. So this means that switch it with row I minus 1, then with row I minus 2, and so on up to row 1. The result will be the following. So we still have summation j goes from 1 to n. Now, when we switch two rows, the determinant changes sign. And here we have I minus 1 switches. So we have -1 to the I minus 1 times the determinants. Now all these zeros will be in the first row. Next, we point out that when we compute determinants, we can do not only elementary row operations, but elementary column operations. So this is because the determinant of a matrix and its transpose are the same, and the elementary row operations on the matrix correspond to elementary column operations on the transpose. This would mean in particular that when we switch two columns of a matrix, the determinant also switches sign. Now I want to move this entry Aij to the top left corner. So this we can do by switching column number j with all previous columns. And now we get that determinant of our matrix is equal to the sum j goes from 1 to n. We have minus 1 to the I minus 1 times. So when we switch column j with previous columns, so we will have j minus 1 switches of signs. And the determinant that we get is the following. So aij will move to the top left entry. And now all these entries will be 0. And we are going to get something here. Now, what can we say about this matrix? So we see that this matrix now is a matrix with a block of zeros. So here, if we take 1 by 1 block in the corner. And what will be the submatrix here? So this submatrix will be exactly a submatrix of A that is obtained by removing row number I and column number j that were moved now to the top and to the left. And so here we'll get the minor mij. And so this expression is also equal to minus 1 to the I plus j. So what we get is we get the sum j goes from 1 to n. So we apply the formula for the determinant of the matrix with a block of zeros. So we'll have minus 1 to the I plus j times aij times determinant of the block mij. But here what we have is this expression is precisely our cofactor aij. So we have the sum j goes from 1 to n, aij times cofactor aij. This becomes a very useful formula for the determinant of a square matrix. As a computational tool, it's not efficient for matrices of large size, unless these matrices have lots of zeros. So if we have matrices with a large number of zeros, then cofactor expansion will be quite efficient. So if we have large matrices with non-zero entries, then we should still proceed computing the value of the determinant using row reduction and elementary row operations.